All right, now that we learned about inductors, we're going to put them in circuits. So, luckily, a lot of the stuff we have to do today is much less work now because it is very similar to capacitors and RC circuits. So, we'll see that the time constant takes a different form, the short and long behavior takes a different form, but we did all the heavy lifting the first time. So, we don't have to relearn everything, we just have to look at some new patterns and what slight differences there are. So, LR circuits, what a surprise. It's got an L and it's got an R. So, to think about what's going to happen, we're going to establish the limiting cases first, like last time, and then we'll do the transient state. So, we said with capacitors, uncharged capacitors started as a wire with maximum current flow, and then they charged up, creating a gap. Inductors are the exact opposite. Because if you imagine I flip this switch and there's currently no current, if I flip the switch, that inductor is going to be very unhappy because you're going to send a huge current change through it. So as soon as you flip the switch, the inductor, of course, waves its finger and says, "Oh no, you don't. You are not changing that current through me." And initially it succeeds. It sends a huge EMF backwards to fight any current. So you actually initially get no current for an inductor. So the inductor pushes really hard back at the battery. It says, okay, don't change the current that quickly. So the battery responds, okay, I'll lower the change. Then the inductor is less unhappy. So it sends back a little less push. So it's still lowering that rate. So it sends a little lower push, and so on and so on and so on, until eventually you've sort of tricked the inductor into changing the current through it by going slow enough. It's sort of like you're boiling a frog by slowly heating up the water temperature. So that's kind of what's happening with our inductor. So the inductor is very unhappy when you try to change the current through it at first. So then it responds by sending a back EMF that slows that rate of current change until it's eventually happy. Well, that sounds exactly opposite of the capacitor. Because at time t equals 0, that inductor waves its finger, "Oh no you don't," and behaves like a gap because it has a back EMF. But when you stop changing the current, the inductor doesn't care anymore. So steady state, you actually do get current flow through an inductor, and it's not opposing anything because you're not changing the current, so it's just a wire. So it is exactly opposite the capacitor case. So we see at short times, inductor is a gap, and at long times, the inductor is a wire. Exactly opposite what the capacitor does. So similarly, that long time case, since it acts like a wire, you can get some short circuits that happen when you have your long time analysis for an inductor. So just be mindful of the difference. These are different circuit components. The capacitor and inductor have opposite behaviors, so just be careful about that when doing these problems. So we're going to do the base case, then we'll do a slightly special one of just what happens when we get more complicated. So this is the most basic L over R circuit you can make. So at time t equals 0, we close the switch for the first time. Well, there's no current, and the battery is going to attempt to go from no current to a lot of current. So of course the inductor is very unhappy as soon as you flip the switch. So as soon as you flip the switch, the inductor is very displeased. "Oh no, you are not sending a changing current through me. No, thank you. I'm perfectly happy with no current." So it behaves like a gap. So if we color code our potential, we see there's no current flow. There's no current flow through this resistor because I have a hole in my circuit. So there can't be a potential difference across it if there's no current. And then that means that the gap, or the inductor, holds all of the potential difference. So if we fill that out in our table, the resistance has no voltage drop due to no current, so it dissipates no power. What about the inductance? Well, the inductance has the entire battery voltage across it, but there's still no current in the circuit, so it does not store energy. It's just extremely unhappy. what about the long time? Well, the long time, after a long time, the battery has slowly stopped sending current at an increasing rate. So the inductor is perfectly fine. No more finger wagging after it is slowly adjusted to the new times. So after a long time, the inductor is just a wire, or a closed switch if you want to think about it that way. So our boomer inductor has finally gotten with the times and has accepted that change is inevitable and eventually succumbs to that. So now notice that in this case, the inductor does not care about the current because it's just current, it's not changing. So all of our potential difference is now across the resistor as opposed to the inductor. So in this case, we had I equals 0 because there was not a closed loop. But in this case, we get a closed loop, so I is just the EMF over Req, which is just EMF over resistance. So what about after a long time? Well, the resistor holds all the voltage drop. It has a current of epsilon over R via Ohm's law, delta V equals IR. Nope, I want to write this as I equals delta V over R. And then the power dissipated. Pick your favorite power formula. I'm going to pick I delta V because we know I and delta V. So we get EMF squared divided by R, which looks like V squared over R, which is one of our other power formulas, not to be confused with centripetal acceleration. All right, what about the inductance? Well, after a long time, the inductance does not care there's a voltage drop through it. Now, that doesn't mean there's no current or energy. There is a current, right? If I go up to my circuit, there's certainly a current that flows around this thing. So it feels the full current. And then what is my energy stored? Well, for an inductor, we don't have 3 formulas to pick from like we did for capacitors. We just have our sort of pseudo kinetic energy, 1/2 Li squared. So we get 1/2 L epsilon squared over R squared. Just plugging in our current into that. Kind of an ugly expression, but still works. So that is our like simplest case of an L over R circuit. It's the inductor opposes the change at the start, and then it does not care, and it's happy, and it's storing energy. Now we have sort of a compound one where it's not just a perfect series, there's some other loops involved. So of course, this isn't really series or parallel because we're combining a resistor in parallel with an inductor. So we just have to look at it at the short and long times. All right, so again, we use our same ideas as last time. This is actually the same circuit that we used in the RC section, which is intentional, so we see the similarities and differences. Or we say it wasn't part of the figure budget. So this is a numeric problem. You're 20 volts. You are 5 ohms. I'm not going to draw anything down the inductor branch. You are 15 ohms. And that's it, actually. So this is our circuit, and again, we know that at short and long times, we can just replace that inductor area with something. So short time. Well, there's no current through the circuit right now, and the inductor is perfectly happy with there being no current. So as soon as you flip the switch, the inductor says, oh no, you don't. You're not changing the current through me. So I'm going to fight the change for a second and be a gap. All right, we can fill in our potentials. High potential hits a blockade, no other way to go. Low potential moves around, hits a blockade, looks around, finds another path. Like that. And then I'm out of colors, so I need an intermediate potential. All right, so what do we notice about this case? Well, this is cut off. This is a hole, right? So this side of the circuit basically does not exist. So that means that all of the current is forced to go around the big loop. So Req is just 5 and 15 in series, which makes 20. So our total current in the circuit is just 20 over 20, which is 1 amp. So we get current flowing in the circuit for sure, but just not in the inductor. The inductor is opposing it. The current doesn't flow through the inductor's branch. There is current in the circuit, just not through the inductor at this time. All right, long time. Well, after a long time, the inductor has fought with the battery, and it has sort of been tricked into allowing current through it, but it stopped changing, so it doesn't care. It's a wire now. So we'll color code high potential, low potential, continues exploring, continues exploring. And notice this is the short circuit diagram because, yep, I got a resistor and I have a complete circuit, but both ends are blue. It's getting shorted, right? Because if current comes over here and sees two paths, one with resistance and the other with no resistance, all of the current takes the resistance-free path. So the 15 ohm is shorted. So that means that our Req is actually just 5 ohms. So my total current is just going to be my battery voltage divided by my resistance, which is 4 amps. And in this case, all of the current goes through the inductor. So that's our short and long time analysis. And now let's put everybody in a table. All right, short times. Well, short times, we have 1 amp of current through the circuit, and that's sort of routed around the whole thing. So my 1 amp goes around the whole circuit, goes through you, and goes through you. So that means that there is 1 amp of current through each of these. And we can get the voltage drop by delta V equals IR, and the power by P equals I delta V. Voltage drop, really easy, right? It's just V equals IR, and I is 1. So you are 5 volts, and you are 15 volts. Power dissipated, I delta V, 5 joules per second, so 5 watts. 15 joules per second, 15 watts. What about the inductance? Well, if we go back over here, it is not the full battery this time. Because notice, my inductor is in parallel with the 15 ohm resistor, which has a drop of 15 volts. And just like we said earlier, or as we've always been saying, 2 objects in parallel, same potential difference. So, voltage drop across the inductor is 15 volts. It is not receiving current at this time because it's fighting it, and the energy stored is 0. Thank you, motorcycle in the background. Very cool. Long time after switch is closed. Well, we see that all the current, all 4 amps of current, goes through the 5 ohm. So we just multiply I delta V and get 80 watts. There is no voltage drop across the 15 because there's no current, so no power dissipated. What about the inductance? After a long time, there's no voltage drop because it's not unhappy anymore. There is a current through it, though. The inductor is part of this short circuit, so all 4 amps of current are going down the inductor's branch. So all 4 amps of current go through the inductor. So what is the energy stored? Well, we have an expression that says U is 1/2 Li squared. So I get half of 30, which is 15. And then I squared would be 16. Sorry, we got to do this in our head. I get 15 times Oh, what is that? Let's just do it the other way. Current through, so square that, I get 16. I get 8 times 30, 240 microjoules. Man, I hope that's right. Should be, because we get half of 16 is 8. 8 times 30 is 240. All right, so we see that the inductor doesn't fully store energy until the steady state. Doesn't oppose current, and opposes changes in current. And there's no change after a while, so it's fine. All right, what about 3? So here's another compound one. In the circuit shown below, we can do the old 2-state switch here, where first we have just a standard L over R circuit. We're going to put it in position 1, then we're going to flip it over to 2. So what's the steady state current through the inductor? Well, it's been in position 1 for a long time. So long time. After a long time, this means L is equal to a wire. So we just have a standard simple circuit. So this means that my current is just the EMF divided by Req. So it's just our standard Ohm's law current. Nothing weird. How much energy is stored in the inductor's magnetic field after a while? Well, this is the same result as earlier. We said that U is 1/2 Li squared. And after a long time, I is epsilon over R. Make sure to square both things. So we get 1/2 times L times epsilon squared over R squared. So I could write this as L epsilon squared over 2R squared if I wanted, just to make it take up less space. Nothing weird there. Then we flip it to 2. So here's where things get strange. So first we want to determine the magnitude and direction of the current through the inductor as soon as I flip the switch. So as soon as I flip it from 1 to 2, so pretend the switch is gone from 1 and it switched to 2, what's going to happen? Well, right when I flip the switch, the current is doing this. Because that's what the steady state current is. It's EMF divided by resistance. And what do inductors do? Inductors oppose changing, we'll say changes in current. That's just a fact. So this means initially I is going to be equal to EMF divided by resistance downwards, because that's what it was doing before I flipped the switch. So as soon as I flip the switch, the inductor is going to keep doing what it's doing. Because again, it went through all this trouble to build up this current through it, but then you flip the switch to position 2, and the inductor's like, oh no, I spent all this time getting my current up to epsilon over R. I'm not changing right now. Of course, it'll eventually change, but as soon as you flip the switch, it's going to maintain that. So this causes an interesting result. We want to find the potential difference across the inductor a short time after the switch is moved to position 2. So let's do that. So our effective circuit in position 2 well, that's a bad drawing. It's going to look something sort of like this, right? If I go back up here, it's going to be a 3R and a 6R. My go-to resistances. So we said as soon as I flip the switch, the current through the inductor is epsilon over R. So what might be helpful is we know that things in parallel have the same voltage. So let's condense these resistors into a single REQ. This is a pretty well-known one. This is a pretty well-known one that 3 and 6 make 2 in parallel. So I have a current of epsilon over R going through my circuit, and I'm pushing that through an effective resistance of 2R. So we actually know that delta V across the inductor is going to be the same as the delta V across this 2R resistor, which is going to be I times R. I, we said, was epsilon over R, and the resistance is 2R, so we get 2 times epsilon. So when I said we get something interesting here, this is why it's interesting. Because the inductor voltage is actually double the battery voltage. So because inductors maintain the current, the inductor doesn't ask the resistor what current to come up with. The inductor maintains its original. So it's actually possible to get huge voltages in these inductor circuits as soon as you flip the switch. So there's a common demo of you can use this inductor to sort of light up a neon gas tube that needs thousands of volts to light, even if your resistance that you need, even if your battery voltage is small. You can sort of step up the voltage by getting a very big resistance over here and a really small resistance over here. Now, of course, that's not constant. Like, you'll just see a big flash and that's it. But inductors can generate high voltages using this technique. Determine the total energy dissipated by the resistor network while the switch is placed in position 2. Well, this is actually pretty easy, because we said that the energy stored initially is this quantity. And there's no extra energy being input into the system when I flip the switch. So if I let it go and the current decays and it gets turned into heat, we know that E total is just going to be U stored in the magnetic field initially, which we said was L epsilon squared over 2R squared. So no fancy math needed, although you could verify it. Like, we're going to learn the calculus from this, and you could verify using calculus expressions. You will get this result, but why bother? It's just 1/2 Li squared. That's actually how we derived the energy formula to begin with. We use this conservation technique. All right, now we'll get a familiar set of equations. So when we look at what we call the transient behavior, again, that's the short and long time behavior, we see our familiar two graphs. We have exponential approach and exponential decay. And also we got the time constant. The time constant is back. And remember, we said the time constant tells you how quickly things happen. Mainly, it's sort of like a 37% life, or more of like a 63% life is more accurate. Because after one time constant, if your current decays, it is decayed by 63%. And based on how the naming of the section worked, you could maybe have guessed that this would be the time constant. That the time constant of an LR circuit is not actually LR. I've been calling it L over R circuits because it is L divided by R is the time constant. And this should make sense, actually, that resistance is on the denominator this time, because, first of all, inductance should go on top. Why? Well, if your inductor is better at fighting change, it's not going to change as quickly. So time constant should increase with more inductance because there's more fighting happening. R goes on the bottom because if there's more R, there's less current. And if there's less current, that means the rate of current change is going to be less. So the inductor isn't as displeased. So the steady state can go on quicker. As per usual, I think we should verify this has units of time. So we can do that. So what on earth is a Henry? So L is a Henry. Great. What is that? Well, we said that induced EMF is L di dt. So this means that L is EMF divided by di dt, which is volts per amp per second. Okay. And we can bring one of those seconds up. So we get volt times second divided by amps. All right, so what is R? Well, R is an ohm, but we said resistance is voltage divided by current, because delta V equals IR. So R is delta V over I. So it's a volt divided by an amp. Oh, that looks nice, because if we actually divide L divided by R, we get volt times seconds divided by amps divided by volts divided by amps. And would you look at that? Volts go away, divide by amps go away. So we're just left with seconds, a time unit. Nice. All right. So now we have, oh, and also we're not talking about combining inductors in series and parallel like we did with resistors and capacitors. I'm not totally sure what the choice is there and why it is. You could argue that these actually should add like resistors. So inductors actually behave like the resistor rules. I'm sure there's some more advanced effect as to why we don't consider this that I am not fluent in electrical engineering enough to understand. Or I just haven't heard of it, I guess. But first, we don't actually combine inductors in series and parallel in this class. All right, so for the circuit shown below, derive an expression for the time required for the current to reach half of its steady state value. So we know that we're going to use one of our parent functions. And what's going to happen? Well, we know that at time t equals 0, you're a hole. So at time t equals 0, we get no currents. But a long time later, the inductor, it's fine. You've slowly increased the current. I guess I'll deal with this current being through me. So we actually want an increase. So we actually know that I is going to follow the following form. We know this is actually going to be the exponential approach graph. Because if we look at our two families here, our current increases over time. So we actually follow that graph as opposed to decrease over time, which is just the decay. Doesn't actually make a difference for this problem, but because of the 50-50 rule, but it's fine. Okay, so let's just do this in terms of tau first, then let's get tau. So we want to figure out how long does it take to reach half of its value. So how long does it take for for I to become 50% of I max? All right. And as per usual, this is an exponential relationship. So your principal value is going to cancel in all of these time-based calculations. It's all about factors and ratios. So we get 1/2 equals 1 minus e to the negative t over tau. Subtract 1 from both sides. We get negative 1/2 equals negative e to the negative t over tau. We can get rid of the negative. So I get 1/2 is equal to e to the negative t over tau. And then we take the natural log of both sides. Oh, gotta write my ln on that side. And again, you can only cancel if ln and e touch, which they do. So we can write ln of 1/2 is equal to e to the negative t over tau. Sorry, just negative t over tau. I canceled that. So this means that t is equal to negative tau times ln of 1/2. Which again, this seems kind of odd because we get a negative time, but remember that log property says this -1 can become an exponent on the 1/2. So I actually get tau times natural log of 2. But tau is not a variable we're allowed to use. You got to figure out what that is. So we'll do that in here actually. We know that tau for this circuit is L divided by Req. And Req is very easy. It's just a 1 and a 2 in series. So it's L divided by 3R. So that allows us to just plug that in down here. So we get the time constant times natural log of 2. So I know I always say this is kind of like the half-life is this time constant, The real half-life, I know we can't see that, so we'll scoot it over a bit here. The real time constant, or the real half-life, is a time constant times natural log of 2. And again, that's like 0.6 something, this ln. So it's slightly less than a time constant would be the half-life. All right, now we got a standard ranking to do. Consider each of the following circuits. Assume all inductors and resistors are identical to one another. So we have resistor, inductor, series resistors and inductor, parallel resistors and inductor. What a surprise, we're ranking the time required to ramp up to 50%. So notice this is really just the capacitor problem, just with a different time expression. So we know that anything regarding time is going to be proportional to the time constant, which in this circuit is L divided by R. So it's an L over R circuit. So we just want to, so we're just ranking L divided by REQ for each. All right, so all of the inductors are L in this. So this is easy. L, L, L. And now we can divide or multiply, or sorry, we can add or use our division depending on which one. All right, this is our base case. We just have a resistor and an inductor. So time constant is L over R. 1. So I guess 1 L over R. Okay, your two resistors in series. So two resistors in series adds like that. So your L divided by 2R. Because L is 1, R EQ is 2. So it's basically 1 divided by 2. So 1/2 L over R. And then here, we have two resistors in parallel. So if you add them by hand, you'd get 1 over 1 plus 1 over 1 to the minus 1, which is 2 to the minus 1, or 1/2. But remember, if you have identical resistors in parallel, they just divide. So here we would get L divided by R divided by 2. So you get a double division, so we can pop that 2 to the top, and we get 2 L over R. So notice, maybe we should bring this out. So we get 1 L over R, 1/2 L over R, and 2 L over R. So rank the time required. Well, the least time required is the lowest time constant. That was, what do we call this? We call this 2. Then 1, then 3. And again, we said that because your time constant was 1/2 L over R, your time constant was 1 L over R, and your time constant was 2 L over R. And it should make sense this is the case conceptually, because circuit 2 has the most resistance, so the current is increasing at the lowest rate because there's the least current. And circuit 3 is the highest because it has the lowest resistance, so it's pumping out the most current, so any changes are going to be large. Yep, you knew it. You knew it was coming. It's differential equations time. So this works exactly the same. The only difference is we have a new voltage drop formula. It's not Q over C, it's L di dt. And this is actually an easier Diff Eq to set up because it's already in a differential. We don't have to do any substituting because we're not actually solving for Q, which made us substitute away I as dq dt. We're solving for I, and there's already a derivative of I in this equation. So we'll do the same thing where we add the battery and subtract off everything else. We don't mess with any signs, no funniness there. We just say the battery supplies an increase in potential, and then you drop across everything else. And if there's no battery, you still write it like this, and then you just cross it off. I call this the phantom battery technique to getting all your signs right. So let's do it. So this is the ramping up current problem where we have no current and we want to figure out what's happening. So let's write the Diff Eq for this. So the Diff Eq says that our sum of the delta V's is equal to 0 around any closed loop. So if I go around the loop, I am going to gain some voltage across the battery. I drop some potential across the inductor, and I drop, or no, the resistor goes first here. Doesn't matter. So I drop some potential across the resistor, and I drop the rest across the inductor. What is delta V across a resistor? IR. What is delta V for an inductor? L di dt. The signs are always taken care of for you by writing the loop rule, and this counts as a differential equation because there's the function I, and there's I's derivative. I's derivative is in there as well. Now let's solve it. So I'm not separating variables. I've had enough of that, and I think you have too. So especially for this like ugly forcing term looking one, we're going to show the clever guess method. So our equation we have that we still have to mess with a bit is this. All right. So again, before we can make a reasonable guess as to our solution, we need to figure out what the derivative is doing. So if I add the derivative term to both sides, I'd get L di dt equals epsilon minus IR. Then if I solve for di dt, I get di dt equals epsilon over L minus I times R over L. And we can simplify this further, or just make it look more readable, as we get the derivative of I is equal to some constant minus R over L times the function I itself. So we're going to use the solving technique we've always done, or at least I showed it in RC. I think this is a much more efficient technique to solve, is by looking at the clever guess technique. So if you want, you could totally say, all right, multiply over by dt. So we get dt. Then we got to divide everybody by the parentheses term. Then we got to integrate. Then we got to figure out our limits. Then we got to simplify. It is an absolute mess. I find it much easier just to use. It's kind of a guess and check. Again, this is just part of experience with differential equations, is knowing what the answers kind of should look like. So we're saying the derivative of a function is equal to some constant minus this constant times the function itself. So what function is its own derivative? Well, that's of course e to the t. But it's not exactly just e to the t, because we get an extra constant in front, and you get factors like that from the chain rule. So we say it is very reasonable to say that if a function is a derivative of itself up to some constant, it is a reasonable guess to say that I can be written as some constant times e to the negative r over L times t, right? The chain rule tells you what goes in your exponent, plus b. And now we do our conditions. So what do we know about this circuit? Well, we know that after a long, long time, the inductor is going to be happy. After a long, long time, the inductor stopped fighting the current. So we can say that I at infinity is going to be the steady state value of EMF over R. So that means that A e to the negative infinity plus B is equal to epsilon over R. So what we can do with that is, of course, negative infinity, that is 0. E to the negative infinity is 0. So we can say this tells us that the constant B is epsilon over R. All right. So now we can go again, because we know that I at 0 is equal to 0, because the inductor is very unhappy at t equals 0. So we can plug in and say that AE to the 0 plus our newly found constant B, epsilon over R, has to be 0 at that time. So we can see that A must exactly cancel epsilon over R, so A is negative epsilon over R. And after that, we've worked out our guess, so we can say that I is going to be negative epsilon over r was our value of a. And then our value of b was epsilon over r. So we can rearrange. And we get our exponential approach function. Now you might be saying, wait, it looks like your time constant is messed up. Because I thought the time constant was L over R. How did you get R over L? Well, remember the parent function looks like 1 minus e to the minus t divided by tau. So to get a time constant, you actually have to create division within your exponent. So how can I do that? Well, I can just flip over the fraction and send it to the denominator. So you could totally stop here. And I would say, yeah, you can stop here. But if you really wanted to like picture what the time constant is, if you had no idea what the time constant should be for an L over R circuit, we can write it like this. And check that it works. So divide by L over R. So we see that we do get the division by L, but also I introduced an extra divide by R, so that pops up to the top here, giving us a numerator as a result. So that's how we can solve this Diff Eq. Now, if you worked through it and actually separated variables and integrated, shout outs to you. Like that kind of sucks. And I really don't like solving that differential equation. I like just using the clever guess method, where we know it's going to be an exponential solution with that constant plus b. And again, the only reason I knew what variable to put in the exponent is because I solved for di dt. So if you're going to guess an answer, the only way you can guess your answer is by seeing what chain rule factor is in front of the function. So my derivative of my function is equal to blah, 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 plus this constant times my function. So I know that goes in the exponent because it's the chain rule. Now, we'll do the discharging case with separation of variables because it's a lot less menacing. So we'll do the same idea here. So we're saying we have a current of epsilon over R through this inductor as soon as I flip the switch. So it must be coming from somewhere else, and then it sort of decreases over time. So let's start with the loop rule. Loop rule says the sum of all the delta V's has to be 0. Well, we can gain some potential across the battery, and then we drop it across both the inductor and we drop it across the resistor. There's no battery in this circuit. No problem. Battery's gone. Voltage across an inductor, negative di dt times L. Oh, sorry, just L di dt. The negative's already built in. Voltage across an inductor, IR. All right, let's solve for di dt. So I get L di dt is equal to negative IR. All right, we can divide, and I would get di dt is equal to negative R over L times I. So again, if we're just guessing solutions, this is really easy to guess. Derivative of what is this constant times itself? Well, we know it's going to be some form of an exponential. And it's just going to be e to the minus R over L times t. And then in front, we put the initial value. But of course, for purists, let's show a separation of variables just to make us happy. So if I separate variables, I can write this as di over I equals negative R over L times dt. And I'm going to integrate, so I'll just call them this little dummy variable here with the primes. Time is easy, right? Time, I start from 0 and I end at t. What about my current? My current begins at epsilon over R and it ends at some value I. Now we do our antiderivative. So U work out to ln. So it's going to be ln I minus ln epsilon over R. But of course we can condense that using the subtract rule or the quotient rule for logs. And this side just integrates to t. As per usual, we can cancel out an ln because E and ln are inverses. So if you put them right next to each other, they cancel. So this gives us I divided by the quantity epsilon over R is equal to E to the negative R over L times T. So I would be epsilon over R times E to the negative R over L times T. But of course, if you really want this in terms of the time constant, we can do that division trick again to see what is being divided in the exponent. And I can get the expected results. So again, notice it does follow the same old form, e to the minus t over tau. Now, again, if you just guess the solution to this one too using the same method, you would get the b term is 0, and you get the a term as epsilon epsilon over r. Wow, force of habit, just saying epsilon 0. So there's both methods of solving a Diff Eq. So both of these work on the ones that I didn't use. So if you wanted to use this technique on the previous Diff Eq to separate, you can. You just get a lot of extra chain rule shenanigans you got to deal with. All right. In the circuit shown below, there's initially no current. At time t equals 0, I flip to this one, which is just our standard L over R circuit. Then after a long time meaning many, many time constants, I flip to position 2. So the inductor goes from storing energy to releasing energy in those two regimes. We want to sketch a graph of the potential difference across the inductor as a function of time. We want to label the value at t equals 0 and the value at t equals delta t. All right, so first let's draw our two circuits. So this is our first sort of regime of the inductor. So at this time, we get our inductor storing energy. So we know that our current is going to build up, and eventually we get our steady state current through the inductor. But initially, it's not that. Initially, the inductor is very displeased that you're attempting to send a change in current through it, so it's going to oppose. So we know that, at least at the start, we're going to have an EMF equal to the battery voltage across it. So the inductor's unhappy, so the battery slows down. And as it slows down, the inductor is less displeased because you're decreasing that rate of current change. So the inductor's like, okay, you can pass some current through me. But then you flip the switch. So what happens when you flip the switch? Well, as soon as you flip the switch, there is a current through this inductor. And we know exactly what it is. It's epsilon over R. So this would be our T2. So as soon as I flip the switch, the inductor again maintains current flow. So as soon as I flip the switch, it's epsilon over R. And this inductor is wired in parallel with this resistance. So this is that high voltage trick from last time, where we see that you're sending a current through it, and when the resistance increases with that same current, you actually get a bigger voltage drop. So we get a huge voltage spike as soon as we flip that switch over, because inductors maintain the current initially. So we maintain that current through a larger resistance. So it causes, actually, instead of it being epsilon, we get 3 epsilons worth of voltage drop at that time. And also, if it really mattered, it would decay slower. But that's the best I'm going to do. Because again, how do I know that? Well, we know that delta V is IR, which is epsilon over R times 3R. So we get 3 times the battery voltage. So again, once again, notice that you can actually exceed the battery voltage. So inductors can also be dangerous and create sparks in that sense, where if you have a quick voltage trip like that. do that. And of course, it'll approach zero eventually because there will be no current through your circuit anymore eventually as we lose our energy. That's an interesting problem. Scoot you over a little bit for visibility. So we actually get a larger EMF when we flip the switch. All right, and last we have a lab question, although we're not going to fully linearize this time. With data, we're just going to give an outline. This was modified from 2023 or 2024. There was an actual AP question like this. A group of students have an unlabeled inductor. How horribly contrived and inconvenient. And they wish to calculate its inductance. They have an inductor that they don't know about, a resistor that they do know the resistance of, a battery that they don't know the EMF of, a switch, and a voltage probe. How they somehow don't know the battery voltage but have a voltage probe, whatever. Draw and label a circuit that students could construct to measure the voltage across a circuit element such that the voltage decreases over time. Because remember, if we're linearizing, we don't want this. This is bad. This is bad for linearizing. We don't want any parent function that looks like this. Because the thing we're targeting when we're linearizing is something we can ln into being a straight line. So we are looking for some sort of relationship that we want the voltage that decreases over time. So we're looking for something. We're looking for this. So we're trying to find something where it decreases. So first let's draw the circuit. There's really only one way to draw the circuit, and we just have to pick where to put the probe. So we know nothing about the battery. We do know your resistance is R. It's some number they know. You are an inductor, who we don't know anything about. And you are a switch that at some point we're going to close. All right, so we want to find the inductance, which means we're going to have to linearize some sort of data, because the kind of goal is linearize, calculate tau, it's easy to find L if you have tau, because you already know R. Because we also know the relationship tau is equal to L over R. So what decreases over time? Well, we have three options. Well, the battery is a terrible choice. The battery's the battery. Do not pick the battery. What about the resistor? Well, if I pick the resistor, I'd be tracking the potential difference across the resistor. So as soon as I plug it in, there's no potential difference because there's no current. But the current is going to build and build and build and build. So actually, the resistor is not the right answer because the current through the resistor builds up like the exponential approach graph. So the voltage will also build because of Ohm's law. So by elimination, that leaves us with the inductor. So why is the inductor the right choice? Well, as soon as I close the switch, the inductor is very unhappy. So the inductor is going to completely fight the battery. So if we actually graph what delta V across the inductor is going to look like as a function of time, we know it's going to be very unhappy at the start, and it's going to be happy at the end. So it's going to decay, which is exactly the type of graph we're looking for this. So that's correct. So what do we actually need? Well, look at my graph. So we are going to close the switch. Well, switch. We can close the switch. And we're going to collect delta V across the inductor versus T for several times using the voltage probe. Because if we plug this in and we start timing it using the probe, it's assumed that this is a very fast acting probe. It has a high sampling rate, so we get a nice delta V versus T table. That's just how we collect it. How can we use it to calculate out? Well, we know that we'll just call it V. VL across the inductor is equal to the maximum voltage across the inductor times e to the negative t over tau. Just like with RC, we said the trick for this was to take the natural log of both sides. So if we take the natural log of the inductor voltage, we're also going to take the natural log of our entire right side. Can't do anything to the left. And we can't do this. You can't cancel unless if ln and e touch. So we got to break you apart using the product rule. Because the product rule for logs says that multiplication can be turned into addition. And now we can cancel that log. So we could get ln of VL is equal to ln of V max minus 1 over tau times t. And all I did is I just rewrote negative t over tau. And to make this more readable in y equals mx plus b format, we can write this as ln of VL is equal to negative 1 over tau times t plus natural log of V max. So now we see we have y equals some constant times x plus another constant. So you're actually the y-intercept, and you are the slope. So we haven't succeeded yet. We have to describe what to do to this. I've taken up a lot of space, so we're going to magically shrink you a bit. Oh, and capture all of it. Fine. Let's try that. There we go. Move you up. I need more space. So what do we got to do? Well, we have to graph ln of V across the inductor versus t. And why is that helpful? Well, it's helpful because the slope is equal to negative 1 over tau. And we also know that tau is equal to L over R. So we can use that to solve for L. So that's our rough procedure for this. All right, suppose instead we only had access to a current probe. If we used a current probe instead of a voltage probe, does this above process still work? Well, again, the key to making it work was the parent function. So let's think about it. What is our current probe going to graph if we construct this circuit? Well, initially the inductor is not happy, so it is going to fully succeed in fighting the current. But eventually the inductor is happy, so it stops fighting it, so we get actually this graph. So no, we can't do that because what does this function look like? This would look like I is equal to I max times 1 minus e to the negative t over tau. So we see, no, this does not work because we have a different parent function. So we cannot linearize. It is possible to curve fit and do things. We just can't do this exact procedure because if I do ln, and ln of this thing is not nice because I can't just cancel the e because of this 1 that's sticking around. All right, so hopefully that was not as new as RC. We see that there's slight differences, but it is really just the same old stuff. So I tried to introduce some new problems where possible, but it is really just the same idea. So that's our inductor resistor circuits. So that just leaves LC, and we're out of here.